Right, and good evening, everyone. I'm Jordan from Group 2, and today we're going to be talking about the bomb calorimeter experiment that we will be doing next week. Okay. Just some quick background on this. The bomb calorimeter is a device that takes a certain sample and explodes it with a set amount of oxygen and transfers heat through conduction to water. That water source will heat up with a delta T, and we can actually determine the amount of heat given off through that water with the delta T. The objectives of this lab are to become familiar with the physical procedures of this project. We're going to be determining the thermal capacitance of this calorimeter, so the amount of heat that the system can actually take itself. That is critical in order to determine the amount of heat that's given off. We're also going to be determining the gross heat from these samples. Every sample gives off a different amount of heat, so we need to have a reference sample in order to further figure out unknown samples. The theory behind this, of course, is that every different sample will give off a different amount of heat. If we have a reference base, then we can move forward with the project. This heat is transferred through conduction from the actual combustion to the water source. It is considered adiabatic and isothermal, so all of the heat from the explosion actually goes to the water. It's important that we keep our thermocouple in the water at all times so we can measure the variations that happen in the water temperature throughout the entire experiment. Okay. The main theory behind this experiment is using the first law of thermodynamics. So the amount of heat into a system is equal to the amount of work plus whatever change in internal energy there is. However, if we have a set base for our calorimeter thermal capacity, we can determine the amount if we have a known amount of heat and we have a measured delta T, we can determine the amount of thermal capacity that our system has. If we pressurize our calorimeter, we can make it a closed system, ensuring that no heat is going to leave the system. An important thing to note, however, is we do have the higher heating value and the lower heating value, which is our heat of vaporization. During every combustion, there will be some water vaporized, and we need to be aware of that whenever we're taking data. Quick overview of lab safety. We are dealing with explosions, so we want to be wearing slacks or jeans. We want to have closed-toe shoes. Also, take our time, make sure everything is measured very carefully. We don't want to add too much sample. We might cause too big of an explosion. We might get inaccurate data. If we have any questions, of course, stop and ask the instructor. Don't proceed if you don't feel comfortable. Our apparatus is going to be a large water bucket holding exactly 2 kilograms of water inside of our housing, which houses igniter wire, and a small sample that will be combusted along with the ignited wire. So we will have heat coming from the sample and also the wire itself, and it's important to distinguish the heat that comes from both of those. The thermocouple we'll be using is a K-type thermocouple, that's what we've been using in all lab. It's important that we keep it at an elevated height inside this water so that it's not touching any of the sides, because that will give us an inaccurate reading. Our motor will be mounted on the side. The motor spins water around the inside of the bucket so that we get a better even distribution of heat throughout the system itself. Outline of this procedure. So bomb preparation is critical along with the water preparation. We don't want to add too much water. We don't want to add too much sample. We want to make sure that we're at a value that is at room temperature to get a baseline reference. The assembly of the bucket and the assembly of the bucket is very important. We don't want any bubbles to form when we drop the bomb in. That can give us inaccurate results as well. Shutdown procedure, we want to make sure that we depressurize the actual system itself. We want to slowly depressurize it, because if we open it too fast, we create positive pressure, we get an actual bomb. Some quick sample calculations. In order to do the actual experiment, I needed a delta T, but we did not have a measured delta T because we're using benzoic acid, which has a known heat of combustion. So we're trying to back solve for this actual value that I've calculated right here. So I've used the thermo textbook and a few online resources to determine a sample thermal capacitance and back solve to find what our estimated rise in temperature is going to be, which is roughly 2.9 degrees, and that can go either Celsius or Kelvin. So we can expect a small raise. There's not going to be a ton of difference. However, when we get to the lab itself, there will be a bit of disparity. Quick predictions. We are going to let it reach equilibrium before we do the combustion itself. I expect several sharp rises followed by a brief steady equilibrium value until it drops back down to its starting equilibrium value. A room for error, we can always add too much fuel, and we can always not allow it to reach equilibrium, which will give us inaccurate results. My references that I use, and does anyone have any questions?